Okay, good afternoon. Let's pick up with the last slide for the recap chapter. Okay, the recap chapter. So we were here. It's not quite the end. That was the slide from the recap. Okay, so now as engineers, we are used to dealing with a wide range of values. Okay, from the very, very small to the very, very large. And so we use unit prefixes to explain or to express our quantities. Now, most of you are probably familiar with the middle of the table, right? Now, don't have to memorize everything. Even I don't have it memorized. The table is very useful, though. Just to give you an idea of how small this is, though. The course is about semiconductor devices, and we talk about microchips. So what exactly is a micro? Everybody's familiar with the millimeter, right? We've seen a millimeter. We can even approximate it. So they're in all our rulers, all our scales. A millimeter is 1/1000th of a meter, 10 raised to minus 3. If you take 1 millimeter, just this small, and divide it into 1000 parts, what you get is 1 micron, 10 raised to minus 6. And very early on, 1 micro came to be known as a micron. There's actually a company, a microchip building company, that's known as Micron. Okay, and that's where the name comes from, microchip. The reason it's a chip is because they are cut out from pieces of silicon wafers. Okay, so that's a micro. You take 1 millimeter, divide it into 1000 parts, and each part is a micron. One of the smallest ones that we have handled is basically our hair. Human hair is on the width or the order of about 75 to 80 microns. We use mechanical pencils, which is 0.5 millimeters. That's 500 microns. And then, of course, tiny cells inside our bodies, very small. If you take that 1 micron and divide it into 1000 parts, each part is a nanometer, 10 raised to minus 9. Okay, it's that small. And that is the current state of semiconductor devices. Our current feature size. I think it's about 3 nanometers or 4 nanometer fabrication process. That's the latest in the world. So we are talking about feature sizes that are on the order of nanometers. And that's 10 raised to minus 9. And then, of course, you would have used capacitors sometimes. You would have come across pico, femto, picofarads, femtofarads, parasitic capacitances, which are very, very small in value. Okay, so that's basically on the right-hand side of the table. On the left-hand side, we have the multipliers. You might be familiar with the kilo, mega, giga, tera. We use these terms nowadays. They're commonly used in everyday life. Megabytes of data, gigabytes of data, terabytes of data. Data centers handle large data sets. It could be petabytes of data, exabytes of data. You as a computer engineer might go to work for a corporation or a company that handles, data in this size. So this is something that you don't have to memorize, but at least the middle of the table should be familiar to you. So that's if you're in a meeting and somebody's talking about petabytes of data, you should have an idea of what they're talking about. Okay. All right, just to show as an example, just to show how big that is, mega is 10 raised to 6, which is a million. Right? So as an exercise or an example, how much is 1 million seconds in terms of days, weeks, or months? Take a wild guess. Anyone? Just a wild guess. Yes. 10 days. Do you know the answer? A very, very good guess. About 11.71 days or so. Or 11.3 days, I'm not sure. Less than 12 days. Means if you had $1 million and you spent $1 every second, you would run out in less than 12 days. Let's go to the next one. Same question. How much is 1 billion seconds? Days, weeks, or months? Student in a previous class said 11,000 days, which I mean, technically is correct. But that's the whole point of using a unit prefixes. Anyone? Yeah, you know the answer. It is more than 31 years. If you are a billionaire and you spend $1 every second, it'll last you for 31 years. The world's wealthiest people have hundreds of billions. That's an unimaginable amount of money. Anyway, as engineers, you will run across these values all the time. Okay. One of the other common places where we use these large scales are frequencies. Your home wireless routers, 2.4 gigahertz, 5 gigahertz, right? Anyway, so that's that slide. And now let's begin semiconductor fundamentals. So before the beginning of every lecture or chapter, there will be some course learning outcomes will be posted right at the front. And so at the end of the topic, at the end of the chapter, once you get done with your reading and your homework, you come back, you take a look at these course learning outcomes, and you self-verify. Do I know how to do these outcomes? How did my learning progress? Okay. At the end, can I define a material or a semiconductor based on certain criteria as an example? So once you're done with your today's lecture, you're done with your reading, you're done with your homework, come back and do a self-assessment using these outcomes. Okay. So use this for self-assessment for your progress. Okay. So this course is about semiconductor devices from a systems-based or application-based approach, right? So we're going to spend a couple of classes, maybe 2, maybe 3 classes on semiconductor fundamentals, and then we'll quickly move on to devices, and then how we can use these devices to create circuits, and then create different systems for applications. So the devices we're going to study are diodes, transistors, which are BJTs, and then FETs and MOSFETs. Hold on. So to make sure, okay. So FETs are field effect transistors, and then we have MOSFETs. The MOS stands for metal oxide semiconductor. It's a sandwich layer that's controlling the flow of current. And these come in 2 flavors. So N type or N channel, the P channel. Most modern electronic devices, almost all of them, are due to the advent of MOSFETs. If you combine both of these on a single piece of die and create your circuit with both N and P type or N and P channel, you get what is known as complementary MOS, because it has both N and P, complement each other. You get a CMOS device. CMOS is something that you definitely come across, right? So it basically refers to the fact that you are using fabrication technology, using N-channel and P-channel MOSFETs to create your circuits. Almost all digital circuits nowadays are created using MOSFET or CMOS technology. Okay, everything that is possible today is due to the discovery, fabrication, manufacturing, and advent of CMOS technology. So before we had, before the invention of these solid state devices, these are known as solid state because compared to the predecessors, they did not have any visible moving parts. Okay. So these are known as solid state devices. But the predecessors of these devices, of these semiconductor devices, were vacuum tubes. So vacuum tube would be a glass tube about this big and probably about, I don't know, 2-3 centimeters in diameter, depending on the size. And these vacuum tubes would have two electrodes. Bottom electrode would be known as a cathode. Top electrode would be known as an anode. And then there would be a filament. All of this would be sealed in a small glass tube in vacuum or under vacuum. The filament would be heated up. Cathode gets heated up because it's in close proximity to the filament. And then electrons are released from the cathode material and they float on top of the surface. Now, electrons have blank charge, negative charge. So if you apply a positive potential difference at the anode with reference to the cathode, what happens? The electrons are floating on the surface of the cathode. They're attracted by the positive charge, and then there is a current that flows through that external circuit. It's a one-way device. It does not work in the opposite direction. And the name from this came from the fact that it had two electrodes, hence diode. And then when they created a semiconductor version of this vacuum tube diode, the name carried over and they still refer to it as a diode, even though there are no more electrodes in a solid state diode. So the name for a diode comes from the fact that it has two electrodes. So it was good to have a diode. They could build circuits with it, but they also wanted to control the flow of current. So they inserted a third electrode, and the third electrode would be on the side. So you'd apply a potential to the third electrode, and it would control the flow of electrons, and you could manipulate the flow of electrons going from cathode to the anode. And when you insert a third electrode, you have a triode. And so they kept inserting more and more electrons. They got quadrode and pentode and hexode and so on and so forth. I think I have not seen something more than 6 electrodes in real life. But I've read that there were, tubes which like 16 or 17 electrodes, but I don't know if they were real or not. As far as I know, that's the story. Anyway, the vacuum tubes were used in the early calculators, computing systems. They were the size of these giant rooms. That was a computer, basically simple calculator systems. And then, of course, a decade or so later, transistors were invented. Then the integrated circuit was invented, and then the rest is history. All right, so the triode has 3 terminals. Transistors, BJTs, FETs, MOSFETs also have 3 terminals. So these are known as 2-terminal devices. So a diode is a 2-terminal device, and a transistor is a 3-terminal device. It could also be a MOSFET, could be a 3 or a 4-terminal device. Okay, so there are multi-terminals in there. So we'll spend, again, as I said, a few lectures, few classes on learning the fundamentals about semiconductors, and then we look at the applications. So the primary application of a diode, again, it's a one-way device. So we use it to convert an AC into a DC. So you apply AC source to a diode, and you build a circuit using diodes. You have DC at the output. And that process is known as rectification, and the circuit is known as a rectifier. So rectifier. We use it every single day. Our chargers are nothing but rectifiers. When you insert your adapter, charging adapter, laptop, mobile, telephone, anything, you plug it into the wall outlet's all AC. All electric power is transmitted in AC because it's very easy to generate and easy to transmit. You've all noticed those long distance power lines going across the city. right? Coming from power plants. It's very high voltage lines that are stepped down. And then by the time it reaches our residences and our rooms, it's 110, 120 volts. But every single device that we use in everyday life, it's all DC, right? All around us, cell phones, tablets, laptops, this monitor, projector, this television screens, the camera, everything, the computers, everything runs on DC. Okay, so again, very simple application, but one of the most important. That's the diode. If you want to go the other way, meaning you have DC and you want to go create AC, you're inverting it. That's the word that they came up with. And so hence, if you convert DC to AC, it's known as an inverter. Now you are familiar with the logic inverter. It's the same word, same English language word, but different meaning. So if you, as an engineer, again, are in a meeting or you're speaking with your fellow engineers, there needs to be some context about which inverter they're referring to. Okay, so you gotta pay attention to the sentence or the topic. These have become, well, where have you seen these or where you might have used this? In cars, absolutely. Battery backups, generators, not generators, sorry, but like a battery pack generator. And that would have an inverter. In California, there's a mandate that you have to have solar on every new construction, right? Some of those homeowners are decided to have battery packs installed. And so there's an inverter that goes along with that battery pack. So the battery is DC, receives solar energy, charges up, its capacity is full. The output of that DC battery pack is given to an inverter, and the inverter outputs 110 volts. There are electric vehicles that have the functionality of dual way charging, meaning they can store energy, and then when needed, they can supply it back to the home. So they can send 110 volts out. An inverter is what allows us to do that, and that is possible with transistors. Okay. Modern cars, as he stated, have 110 volt outlets. You can plug in a charger directly into that outlet. My car is 15 years old, so I don't have one. Many years ago, I purchased an inverter for like $40. And you can, it comes with 2 power outlets. You can just insert it into that our power outlet, 12 volts DC, and you can have 110 volt outlet in there. All right, so that's 2 of the primary applications. Then the other important application is to use the transistors as an amplifier. This is the symbol for a microphone. Not very commonly used, but that's a technical representation of a microphone. Okay. So if you think about this, this is a microphone right here. It captures the sound, right? It captures the sound of my voice, the acoustic waves. Sound waves are converted to electrical signals. The signals are very weak. The signals are fed into it, into the circuit that's here in the headset, and then it wirelessly connects to the receiver. So this wireless signal, it's encoded, sent to the red, it's decoded at the end, goes into the computer, and now it needs to be made stronger. That happens with an amplifier. Okay. So we look at amplifiers too. Again, this is also one of the most important applications for transistors. Remember, I just said triodes had a third terminal to control the flow of current. And so transistors and MOSFETs, they have a third terminal, and that allows us to control the flow of current between the other 2 terminals. And that is what allows us to create an amplification. We can use these devices to implement digital circuits, right? Pretty much everything we use nowadays are digital circuits, right? Binary number system, zeros and ones. And then circuits, memory circuits that can store and retrieve data or info. I would consider them as a subset of digital circuits, right? Something that can store data is a digital circuit by default. And lastly, not lastly, it was one of the other important applications is for energy transfer from photons to electrons, solar power generation. So your photons, they have energy, and they're incident on a semiconductor device that is specifically created for that. That energy from the photon is transferred to the electrons, and the electrons are now free to move. Okay. The energy transfer is not very efficient. A lot of the energy, a huge chunk of the energy is lost in translation. The solar cell's efficiency is very low. Okay. But it's pretty much free energy, right? Okay, so these are some of the most common applications. Let's go to this slide. Everybody knows or is familiar with this. We are focused somewhere in the, well, it's not the middle, but to the right of the middle, which is column 3, 4, and 5. Okay, 3, 4, and 5. And specifically from column 4. So let's first classify materials. Okay. Based on electrical ability, we can broadly classify materials as conductors, insulators, or semiconductors. Okay, so based on electric ability, broad classification could be conductors, insulators, or semiconductors. Okay, semiconductors. Most conductors are metallic metals which have luster. They're malleable, they're ductile. You can create various shapes using various processes. They are very good conductors of heat. They are very good conductors of electricity because the electrons are very loosely bound to the nucleus. So we're going to talk a little bit about the atomic structure and subatomic particles. So again, the electrons are loosely bound to that nucleus in metals. And they're loosely bound, they are free to move. When they move, they are conducting charge. So they are moving charges. And when charge moves, we say it's electric current is flowing. So in metals, it's very easy because the electrons are very loosely bound. There's a huge number of electrons that are available for conduction. Insulators, the exact opposite of metals. They do not have luster. They are brittle and they are very poor conductors of electricity. Okay, hence insulators. And then there's a third classification of materials that's somewhere in the middle. They have free electrons, but not as many as metals. Hence the name semiconductors. Okay, hence the name semiconductors. And one of the most common semiconductor is, that was very quick, silicon. Silicon is the second most abundant element on this planet. Okay, the earliest actually not the earliest, the first semiconductor devices, the first diodes, the first transistors were all made out of germanium. Because at that time, germanium was easy to process. This was just at the beginning, so it's like the late 1940s, early 1950s, which is right here, column 4. Silicon and germanium. Okay. But then silicon was being investigated at the same time. They devised a method to obtain pure silicon. And once that was in mass production, they realized how easy it is to actually work with silicon. Well, not easy in the sense compared to germanium. So low cost, abundance, and it has excellent, its oxide has excellent thermal and electrical insulation properties. Okay. So I'm going to pass out a few show and tell items. Well, actually, let me talk about something first. So we talked about silicon, right? So let me give you a real life example. When you create semiconductors with these, when you create devices with these materials, you require special processing facilities. These facilities are known as clean rooms. Perhaps you might have seen a visual image or a video where you've seen people gowned up in white bunny suits from head to toe inside like white looking rooms. Anyone? Yeah, sometimes you might have seen an image. Those are known as clean rooms. They are literally clean rooms because when you're working on the order of micrometers and nanometers, tiny dust particles that we can't even see are the size of huge mountains. Microchips are nothing but, you've seen PCBs, right? PCBs are like you have components mounted and all you have are wires running all across the place. That's a microchip. That's all it is. You have components in there. It's integrated into one piece of die or semiconductor. And then there are wires running all across the place. So if you're running a wire from point A to point B and there's a huge mountain in the middle, your road's not going to get built, right? So you need a specialized facility to do that. So there are very few companies who specialize in this. The reason I'm talking about is because it's an avenue, not an avenue, but there are openings for computer engineers to go work in some of these facilities. So that's an avenue that you may not have explored because you may not have been exposed to it. So that just happens to be my area of specialization, by the way. So semiconductor fabrication is a highly specialized skill set. Very few companies in the world can actually do it. Intel is one of the most famous ones. Intel stands for Integrated Electronics. So early on, there were these researchers who were working near Silicon Valley. They came up with something, Bell Labs, and they broke away and they went to like IBM. They started some other companies. A few other people from IBM broke away. They started Intel. And then a few other people, a few years later, broke away from Intel and started AMD, Advanced Micro Devices. So Intel and AMD were the two primary manufacturers for a long time, x86 architecture. So they would design and fabricate their own chips. There are very few companies in the world who would do it. Texas Instruments was one, but then they moved out of doing that in a large scale. There was a National Semiconductor. There's companies in Japan who used to do it. And then another big name now is Samsung Semiconductor. They do it. They design and build their chips. Okay, so very few companies actually build their own chip. The simple reason is it's very expensive. Each machine or each piece of equipment that is required for one single process costs like tens of millions of dollars. The latest photolithography machine is about 100 million. You need at least like 10 of these machines in one room. And so right there, your cost is like hundreds of millions in just one room. You could have like 10 of these rooms on one floor, and you could have like multiple floors in that building and then multiple buildings in that facility. And you add that up, the lowest cost of entry is about $20 billion. It's a huge amount, right? We just saw how big it is. So $20 to $30 billion, and it takes 3 to 4 years for these facilities to come online. If you've been keeping up with the news recently, in the last few years, there was a big push in the US, pretty much worldwide, to have ramp up their own fabrication facilities, right? So TSMC is building a facility in Arizona. A few years ago, it's still not online. Intel is planning something in Ohio. That's still not online. It's still being worked on. Okay, it takes a long time for these to come up. So by the time you graduate, maybe you might want to look into something like that. One of the most famous ones nowadays for fabrication, or the most advanced technology, is with TSMC. And that was very unique at the time they started, because at that time, every company was designing and building their own chips. Nobody else was doing like custom thing. And they were one of the first ones to do it. And so all across Taiwan, you have these companies that specialize in built to order microchips. As TSMC, Taiwan Semiconductor Manufacturing Corporation, is the most advanced one. Okay, they take these designs from Apple, NVIDIA, Qualcomm, and they take these designs and they are the ones who make or build these microchips. So I'm going to pass out something. How many of you know that Cal Poly has a clean room on campus? Some of you do, so that's good. These wafers, these are silicon wafers. These are actual silicon wafers with actual diodes and resistors that were built by Cal Poly students right here. There's a class that we teach. It's a 400 level graduate class, not graduate, sorry, 400 level undergraduate class that students can take. They come into the clean room and we work on processing every single week, every single class. And at the end, we have diodes and resistors. These are 4-inch silicon wafers. And then I also have, these were given to me by an E student a few years ago, a few quarters ago. I wouldn't do that. I mean, if I drop it like even from this height, like an inch or two, it could shatter and break. So I'm just going to pass these around. You can handle it safely. They were processed. These are 8-inch production wafers. So again, it's a fascinating field. That's what I did my master's and my doctoral dissertation in. But that's silicon material. Yeah, that's silicon material. And when we are building devices using these semiconductor materials, we need it to be completely free of contamination. So we refer the terms we use, pure and impure. So purity and impurity. So it's impossible to get anything ideal in this world, right? So it's usually like 99.9999% pure. Okay, there's always going to be some impurity in there, whether it's like boron or like, some sort of impurity in there. Okay. So that's silicon. Okay, we have germanium too. I've never worked with germanium. If you have a semiconductor device created simply from one material, it is known as it's not known as anything, but we just refer to it as single intrinsic semiconductor. That's from column 4 of the periodic table. Column 4, meaning it has 4 electrons in its outermost shell that is orbiting the nucleus. Now, we can also make compound semiconductors. And compound semiconductors are when you take 2 or more materials, fuse them together, and you have compound semiconductors. I have no expertise. I've never worked with compound semiconductors. I had a roommate who worked with gallium nitride, but I never did. So you have silicon and germanium. They're single intrinsic semiconductors. And then you have gallium that is fused or mixed with other elements, and we create compound semiconductors. If the compound semiconductor has 2 elements, it is known as binary. If it is more than 2, like 3, it's ternary. Typically, they are from column 3 and column 5 or column 3 and column 4. Okay. And again, as I said, I have no personal experience of working with it. Most of my experience has always been silicon. So when we use gallium, one of the interesting things that happen is release of energy. Okay. In general, when electrons move, current is flowing, energy is being transferred. Electrical energy is transferred. Obviously, it's not a 100% efficient process. So a lot of it, or some of it, is released as heat, released as thermal energy. So electronic components get hot. Your diodes, if you keep current running through it at a very high level, are going to get hot. So you might have maybe experienced that in the lab. If not, we'll try and do that in the lab. You will see it gets hot. One interesting thing happens with some semiconductors is that they release a little bit of heat, but they also release a majority of their energy as light. So if you build diodes using gallium arsenide, gallium phosphide, or gallium arsenide phosphide, they emit light in addition to a little bit of heat, and hence they are known as light emitting diodes, LEDs. So again, depending on the material that we use, we can have different colors for LEDs. Okay. And that should also be part of your lab kit. Why is this? All right, let me just do it this way. All right, so those are compound semiconductors. Now, there's one more thing. What is this element at the top? Carbon also is from column 4. It has 4 electrons in its outermost shell, yet it is not a semiconductor. Because there is another criteria that must be satisfied. And that's where the subatomic particles come into the picture. That's what we'll talk about. There is something known as energy band gap or band gap energy. Both are very valid terms. Okay, you might see it referred to as energy band gap or band gap energy. So electrons, when the subatomic particles are orbiting the nucleus, they are held or they are bound to the nucleus with certain amount of energy. If an electron is in that space, in the valence shell, meaning the outermost shell, it has the ability to acquire some energy and jump up or move up and be available for conduction of electricity. So if it's bound and it's occupying a state, excuse me, it cannot occupy a random position or random level. The theory is that they cannot exist outside of specific energy levels. So the energy or the energy bands for atoms is quantized. It's discrete levels, and they're all quantized. So the electrons can exist only in those specific states. Okay. So based on this energy value, we create something known as energy band diagram. Now the bottom is EV, valence energy, meaning the electrons have enough energy to stay in the valence band. But if they acquire enough energy, they can jump to the conduction band and they are now free to conduct. Okay, it's not a physical jump, but they're just acquiring sufficient energy. But this is what happens when photons are incident on that semiconductor diode. The photons are imparting energy to those electrons. The electrons acquire that energy and they are now free to conduct. Okay, but this is a material property. So there is a gap in the value between the valence and the conduction energy levels. This is known as the energy band gap. Okay, energy band gap. And for silicon and germanium, that energy band gap is less than or equal to 1.1. For silicon, I believe it's approximately 1.12 electron volts. For germanium, I believe it's less than 1 electron volt, 0.6 or 0.7 or something. I think we have the number somewhere in the next slide. Yeah, 0.66. And silicon is 1.12. Okay, so 0.66. For carbon, however, that energy band gap is greater than 5. I believe it's 5.3. And that is insurmountable. You could never impart enough energy. I mean, you could apply thousands of volts perhaps, and maybe it could, but at that point you have secondary other effects. So you could probably blow everything up. Right? So there is a gap between the energy levels, and that gap in silicon and germanium, we can overcome by external application, but in carbon, we cannot. Carbon, by the way, exists in nature in, well, two of the most common ones are graphite and diamond. Under tremendous pressure and temperature, carbon atoms realign and they form a stable structure. You get a diamond. That happens very deep under high temperature and high pressure, right? So your diamond mines. But the scientific principle of carbon atoms realigning and creating a stable structure is also used in the lab. You can pass a specific type of gas that contains carbon, typically like methane gas or something that has carbon in it. And you have a chamber. This process is known as chemical vapor deposition, CVD. Gas comes in, you adjust the pressure, you adjust the right temperature, decomposes into carbon atoms. You have a seed material on a sample wafer. Those carbon atoms go attract on the seed material. And now you have a diamond film and you can grow diamonds in the lab. That's basically lab-grown diamonds. Again, semiconductor technology. And that's why carbon is not a semiconductor. All right, let's start here at 0 Kelvin. Everybody, I'm assuming, is familiar with 0 Kelvin. Absolute zero, right? Minus 273 degrees C. It means it's so freaking cold, I can't move. I can't move, I can't think, I can't do jack. Nothing happens. Everything is frozen in place, right? So if you have silicon lattice structure, each one of these is a silicon atom, by the way. It has 4 electrons in its outermost orbit, and each silicon atom shares 1 electron each with 4 neighboring atoms. Okay. Thus, they have a stable structure. They have 8 atoms between the 5 silicon atoms. And so every silicon atom is sharing 4 electrons each, and now you have a stable structure. At 0 Kelvin, everything's frozen in place. All the electrons are in their spot. They're all around the nucleus. They are bound to the nucleus. They're not going anywhere. Okay, so far so good. Now let's say the temperature increases. It goes from 0 Kelvin to 10, 20, 30, 40, 50, 60, 70, 100, around 100 Kelvin or so. Some electrons acquire enough energy, thermal energy, to break free of their bonds. Okay, these bonds are known as covalent bonds. Covalent bonds. And some electrons acquire enough energy to break free of their nucleus, and they're now free to move around the crystal lattice structure. That atom is now ionized. Okay, this happens. This is still below freezing, but it's above 0 Kelvin. Okay, you all with me so far? Now let's say the temperature rises even more. So more and more electrons are acquiring enough energy to break free of their bonds, and the number of electrons keeps on increasing, right? We come up to 0 degrees C, we cross 0 degrees, 10, 20, 30 degrees, 40 degrees, 50 degrees. Let's say room temperature, 27 degrees C, which is 300 Kelvin. There is a specific number of electrons. We have an equation to get an approximate, and we call that a specific number of electrons that will be available for conduction because they have all broken free of their bonds. So there are electrons that are available. They have acquired enough energy to now go from the valence to the conduction level, and they're available to they are free to move around in response to an electric field. But the number of these electrons is not sufficient to classify it as a conductor. Even though the number of electrons could be 10 raised to 13, 10 raised to 14, that's a huge number of electrons. It's still not sufficient. In a metallic or in a metal, right? In a metal, there is no band gap. The valence and the conduction bands overlap. So there are electrons that are available in huge numbers for conduction at any given point in time. Okay. So again, as temperature increases, more and more bonds are broken, and you have more and more electrons available for conduction. But here's the thing that happens. Let's say you have an electron, right? You have an electron in all these spots, and there's an empty spot right there. Okay, there's an empty spot. So this electron could possibly acquire enough energy to jump into this empty spot. Okay. Now, this empty spot was created because an electron moved out. It broke its bond and it moved out. What is left behind in its place? An empty spot. And I don't know who came up with it, but again, maybe they didn't, I don't want to say they didn't have any imagination, but it's called as a hole. It's called as a hole. Now, in semiconductor physics, when we deal with these devices, we refer to electrons and we refer to holes. So holes are just empty spots that are created because an electron has moved away. But it helps to treat the hole as a subatomic particle in its own right. Okay, so throughout semiconductor devices, semiconductor physics, you will come across terms that say electrons are moving and holes are moving. Holes are carrying some charge, electrons are carrying some charge the other way. And so it helps to treat the hole as a particle in its own right. And that hole is said to have, positive charge. Because when an electron moves away, that spot is still bound to the nucleus. The nucleus now has one extra positive charge. So that empty spot or hole is associated with that positive charge. Okay. So electrons have negative charge, holes have positive charge. So coming back here. If in the first spot on the left, there was an empty spot due to an electron moving out somewhere, that electron has a specific lifetime, meaning it moved out, but it's roaming around. It's arrived at the party, but there's nothing to do. It doesn't know what to do. If it sees an empty spot, it might go jump in there. Okay, so that's known as a carrier lifetime. It left the spot, it became a carrier. It's available for conduction. But then it sees an empty spot, goes back in there. So it's now recombined. Empty spot is gone, electron is gone. It's called recombination. And the amount of time it takes to move from its original spot to the empty spot is known as the lifetime of that carrier. Excuse me. Okay, how many minutes? Oh, we are almost out of time. Okay. So that's holes and electrons. So if this electron moves to the left, it's going to create a vacancy right here. That means this hole is now occupied and it's moved towards the right. The electron moved towards the left. The hole was here, and now it's here. So again, it helps to treat the hole as a particle in its own right. Electrons moving towards the right, holes moving towards the left. Electrons can move anywhere in the structure, but holes are localized. Okay, holes are localized. So for every empty spot, an electron can move in, and thus the hole can propagate throughout the structure. So electrons are moving in one direction, and holes are moving in the opposite direction. Okay, holes are moving in the opposite direction. So there is an equation that we can use to approximate the number of charge carriers that are present. Okay, and that's basically given right here. N stands for electrons. P stands for the number of holes. I guess N is for negative, P is for positive. And I stands for intrinsic. So intrinsic semiconductor. The only energy that is applied to an intrinsic semiconductor is thermal energy. That's it. Meaning if you are at room temperature, there are a certain number of electrons that will be available. Right? So this equation is NCNV, or root of NCNV, e raised to minus EG over 2 kT. Let's take it one term at a time. EG, see, these are all material dependent quantities. They are constants to a certain extent. They are constants. EG is the energy band gap. We already talked about that, right? NC and NV are the density of states. These are the number of states that are present, number of states of energy that are present in either the valence or the conduction band. Okay, and again, those are fixed, or at least they're constant. So they're given in this table. 300 Kelvin is 27 degrees C. We consider that as room temperature, nice round number. So 300 Kelvin, NC, NV, and EG values are given. We are out of time, so if you have to leave, you can leave. I'm just going to record for a minute or so. And then we have K and T. K is the Boltzmann's constant, and T is the temperature. So it's basically, you have 3 of the 5 values. Actually, you have 4 of the 5 values, because K is a constant, and so are these are the 3 terms, right, from this table. The only unknown would be temperature, meaning if there's a question saying that calculate the number of electrons that are present at like 400 Kelvin, simply look up the table, plug in the numbers, plug in the temperature, and perform your calculation. Okay. So again, you don't have to memorize the equation, but you certainly have to understand what the equation does. Yes. T is in Kelvin. The question being asked is the units of T in this equation. It's in Kelvin. Boltzmann's constant is right here. I know it's tiny. See, it's joules per Kelvin or electron volts per Kelvin. And so multiplied by Kelvin, it's out. And then you have electron volts divided by electron volts. Okay, so that's 8.617 is what you would use. Okay, 8.617. Yes. Electron volts, yes. Question being asked is, do we always measure band gap in terms of electron volts? The answer is yes. Electron volt is basically the amount of energy that is required to move an electron through 1 volt. Okay, that's a measure, 1 electron volt. All right, so let's stop right here and we'll end class here today. If you have not yet read the announcements, again, I posted one yesterday, last night. Lab kits were available starting at 8 o'clock this morning. You can pick it up anytime you want, either today or on Monday. There's a homework and a reading assignment that's due over the weekend. If you have any questions about that assignment, send me an email. I'd be happy to answer. Tomorrow, my schedule is a little busy, but I'll still be able to answer emails. And Sunday, I'll have plenty of time. Yes. Yeah, the lab kits are available. Yeah. I posted the announcement yesterday on the Canvas website. Yes, the reading is extra credit reading. That is also on Canvas available. All right, thank you. Who has my 8-inch silicon wafers? Let me stop recording. All right.